That's me. You're probably wondering how I got here down at the bottom of this math hole. Well, it's a tale as old as Tom. I stayed up late, I found an unsolved math problem on the internet, and then I spent months trying to solve it myself. And this is not the first time that this has happened. Arguably, I'm still in other math holes. Now, I like to make YouTube videos at my own pace, which is about one per year. But it occurred to me that it might be a bad idea for me to wait until I've solved this problem before I start making a video about it. And there's already a lot of interesting things to learn or be upset by, even if we already knew them. So here's part one of the story. It begins with a hostile and seemingly easy question. So, how big is the unit cube? 1? Well, let me ask you this. Where is the unit cube? 0? Actually, let me ask you this. How big is the unit sphere? Also 1, right? And where's that? Also 0? Well, it turns out that canonically the unit cube has one of its vertices at 0, 0, 0 at the origin, and its opposite corner at 1, 1, 1. And that makes sense. But the unit sphere is centered at the origin and extends in each direction by 1 unit, which means it has a diameter of 2. So it's actually a lot bigger than the unit cube, which I think is surprising. It seems that these two basic canonical shapes actually use the word unit differently. In one case, it's like the side length, and in the other case, it's like the radius. And so you can easily fit a unit cube inside a unit sphere. Now, 2 won't fit without overlapping, but you could ask, what's the configuration of cubes that yields the smallest sphere that contains them? And for 2 cubes, that is, in fact, to place them side by side, like you'd expect. For 4, you've got this, which makes sense. Once you get beyond a couple cubes, the arrangements here get pretty gross. For example, you might think that the solution for 6 looks something like this. That would be nice. But in fact, a better arrangement is this monstrosity. I found this by computer search. Namely, after trying myself, I looked it up on the internet and found that someone else had solved it. And we don't know if it's the best, but we know it's better than the regular one. Oh, I love it. Platonically. A great, beautiful math result is appealing to me, but I think that what really titillates me is when the problem is beautiful, but the solution is upsetting. I call this a Platonic horror, in contrast with man-made horrors like the conventional unit cube and unit sphere apparently use the word unit differently, or the x86 instruction set, or the Unicode code point FE18, presentation form for vertical right white lenticular bracket. This is clearly man-made. Aliens would never think to spell the word bracket wrong in the formal name of a Unicode character. But they definitely would think of putting cubes in spheres, and that means somewhere out there, if aliens exist, there's some other math pervert writing Sigbovic papers about this kind of thing for their equivalent conference. And I like that idea. Anyway, now that I've gotten the dice in sphere pun out of the way, I can move on to the real topic of this work, which is dice in dice. All throughout history, we've had the problem that rich and powerful people decide that they want to wreck the world. And I don't really understand this. If I were super rich, I would just hang out with my smart friends and do math, right? One rare example of this seemingly working out well was Prince Rupert of the Rhine, who is a grandson of Mary, Queen of Scots. And this guy, after retiring from being a war sailor or whatever, he, quote unquote, converted some of the apartments at Windsor Castle to a luxury laboratory, complete with forges, instruments, and raw materials, from where he conducted a range of experiments. Now that's what I'm talking about. A math and science castle is a good use of the monarchy. You may have heard of this fellow before. He's the one that learned about Prince Rupert's drop and then didn't protest when people attributed its invention to him. And I imagine Rupert on a pleasant evening, hanging out in the pub, talking about math and exploding glass with his friends, much like I do today, except he was drinking nasty 17th century beer. And he came up with the following question. Can you take a cube, say the unit cube, and pass it through another cube of the same size? Now, superficially, that sounds ridiculous because normally to put something through something else, you want to put a smaller thing through a bigger thing. And these are 2 cubes of the same size. But incredibly, this does work. If you take the cube and point one of the points at you, then its shadow is like a hexagon. That's the big way. And then if you just look directly at one of the faces, its shadow is a square, that's the small way, and this square does fit inside the hexagon, just barely. And when you cut the hole, the resulting shape looks like this. This weird sharp donut. I'm going to call this the residue. Okay. And so 375 years later, I'm up late reading the Wikipedia article about the dodecahedron, my favorite Platonic solid. And I'm reminded by this sentence: the dodecahedron, like the other Platonic solids, has the Rupert property, that the cube is not the only thing that can pass through itself. And that's very pleasant. Let's talk about the Platonic solids for a sec. I just love these things, platonically, but also sexually. There are only 5 Platonic solids: the tetrahedron, the cube, the octahedron, the dodecahedron, that's my favorite, and you'd think I'd be better at drawing it by now, but it is a tricky one, and the icosahedron. Now, these things come in pairs or duals, where the vertices and faces are in correspondence. So for example, if I take the cube and I put a point at the center of each of its square faces, and I connect those up, I get an octahedron, and vice versa. So the cube and octahedron are dual, the dodecahedron and icosahedron are dual, and the tetrahedron is dual to itself. Now, aliens definitely know about these shapes if they've done any math at all, although they probably don't call them Platonic solids, unless perhaps Plato wasn't all that he seemed. And it's a little mysterious that there are only 5, but it's not that hard to understand why. So remember, if you take a 6-sided hexagon, which is the only kind of hexagon, these actually tile the plane if you put them next to each other. And we can see why if you look at the place where 3 of these touch. The angles there are each 120 degrees, which adds up to 360 degrees. So you've used up all of this space. There's no way to wrap around. Compare the dodecahedron, where the internal angles are 108 degrees. So 3 of them together makes 324 degrees, which means that they can curve around. But you couldn't fit 4 pentagons, and if you only had 2, that wouldn't make a solid. So 3 is the only way. And similarly, there's only one way to line up squares around a point, so that's the cube. And it turns out there are 3 ways to arrange equilateral triangles around a point. So that's why there's only 5. You might find yourself wanting a sequel to the Platonic solids because they're so nice. And there are some related polyhedra that we can have if we just relax our constraints a little bit. First, let's talk about the Catalan solids. These are convex solids like the Platonic solids, whose faces are polygons. And here we require that all of the faces are exactly the same shape, which we call face transitive. One way to think about that constraint is if you had paper cutouts of each of those shapes, you would only need one kind of shape in order to tape them together. But the faces aren't necessarily regular polygons. And for a similar reason that there are only 5 Platonic solids, there are only 13 of these possible. And then we have the Archimedean solids. These are convex solids that are vertex transitive. And one way to think about what that means is if we were to 3D print little connectors for sticks, you'd only need one type of connector in order to make these solids. There are also 13 of these, and as you might have guessed, because of this correspondence between faces and vertices, each of the Catalan solids is dual to one of the Archimedean solids. And the Platonic solids are really like the intersection of both of these groups, although we don't count them that way. And that's why Platonic solids are dual to Platonic solids. It works out beautifully. It's schlovely. But get ready to start feeling a little upset. So remember that the dodecahedron and the cube, and in fact all of the Platonic solids, have the Rupert property. They can pass through themselves. And if you keep reading this Wikipedia article, it will say, it is conjectured that all 3-dimensional convex polyhedra have the Rupert property, which sounds really nice, and I might have even gotten to sleep if I had just stopped reading at that point. But then it just casually throws out a line like, of the 13 Archimedean solids, it is known that at least 10 have the Rupert property. Like, there's 3 more. Did nobody check? It doesn't even seem that hard. So that started to bother me. How could it be the case that we've conjectured that this holds for all convex polyhedra, but only know how to do it for 10 of these really well-known solids? But even worse, down here we have the duals of each of those Archimedean solids, which are the Catalan solids. And if you keep reading, you'll find that of the 13 Catalan solids, it is known that at least 11 have the Rupert property. And even more annoyingly, the Archimedean ones that are solvable, their duals are all solvable. But then also the dual of the Snub cube, which we don't know a solution to, is solvable. So this just doesn't seem right. So there goes my chances of sleeping. This is, in my mind, whoever left these here, it's like perfect nerd sniping, like nerd landmines. And it worked. I thought it's totally plausible that not that many people have tried seriously this problem, and I'm definitely not the best mathematician to have tried, but it's plausible that I might be the best programmer to try, or at least the one with the largest and hottest GPU out there. I always try to buy these ridiculous beasts for my programming projects and other things. The 4090 is no longer the fastest, but I think it is the world's physically largest GPU. It's just, you have to plug this thing in 6 times. I literally broke my computer trying to get it in the case, so I had to buy an entirely new computer. So I thought maybe I can find solutions to some of these 5 unknown polyhedra, which I'll call the wish list polyhedra. And if I don't solve it, at least I'll have learned something, because it just doesn't seem right that we would think it's true for all of them, but not find it for these 3 simple ones. And anyway, I could whip this up in a day or maybe a weekend, and I'll just put it aside if I can't solve it. Well, you can imagine how that turned out. But good news, I have a lot more to tell you. Now, I should mention the reason that we know that some of the PAC polyhedra have the Rupert property is because of the related work. And, you can read this. I did not read this. I don't like to get spoilers when I'm trying to figure something out. It is part of the fun to rediscover things. That's why it's called research. So I've described the Rupert property informally, but in order to get into any detail about this, we're going to need to say what we actually mean. And we will get into detail here. This whole video is going to be about cubes and dodecahedra and stuff like that. So let's get more precise. What do we mean when we say that a shape can go through itself? So first of all, this idea of convexity is going to come up several times. The 3D solids we're concerned with here are convex. Basically, this means it doesn't have any indentations. One way to think about this is that you have a set of points, those are the vertices, and you kind of shrink wrap the surface of the shape is the minimal surface that contains all those points. And we're specifically concerned with polyhedra here, where the faces of this shape are flat. So I'll take 2 copies of this convex shape, and I need to arrange them in such a way that one can pass through the other. And I'll call the one that goes through the inner one, and the one that has gone through the outer one. I have the freedom to move these shapes around and to orient them however I want. This is a rigid frame, no stretching, no flipping. It's what you're thinking of. Just move the thing around in space. And then once they're set up like this, I'm going to project both of them along the z-axis. I just need to pick some axis. Z works well. This is an orthographic projection, so everything is not, there's no perspective. Every point is just projected onto the xy plane, and both of the shapes create a shadow, the inner shadow and the outer shadow. And the question will be, is the inner shadow inside the outer shadow? Now, this is hard to draw from the side, and I did a terrible job. It looks like it's not going to fit. So I'm going to use the standard computer graphics convention that we're looking down the z-axis from the top. And the inner shape is kind of coming out of our eyeballs. And then we'll just be thinking about what the shapes look like, the shadows, on the xy plane. And that's going to basically be the screen. And this makes sense because when you move an object along a straight line, the shape of the hole it cuts is the same as the shape of its shadow. So that's basically the definition. Some clarifications. 1, when I say that the inner shadow is entirely inside the outer shadow, I mean that it's strictly inside, so it can't touch the boundary. If you let them touch, you'd have 2 problems. One is that in the leftover shape, the residue, you would have a tiny sliver in your donut in the side, so it wouldn't really be a proper hole. Or at least you and I disagree on what hole means. But if you allow touching, you get a worse problem, which is that the Rupert property becomes trivial. Because now you could take any solid and just put 2 copies of it in the same orientation along the z-axis, and they're going to have exactly the same shadow, so it fits cleanly through and leaves nothing behind, and this is not what we mean. This will turn out to be a pain. because we're going to frequently use inexact, like floating point representations. So these trivial solutions will look really close to real solutions. On the other hand, the fact that they can't touch is kind of nice because it means that if there's a solution, there must be infinitely many solutions, right? There's a distance between the inner and outer shadows. Therefore, I can move a little bit along that distance and find another solution. And this is one of the reasons why I thought it might be computationally tractable. Like it should be locally smooth. That said, just because it's a finite distance does not mean it's big, and we'll see some examples where it is not big. Okay, now some observations. I said I have an inner frame and an outer frame, so I can rotate and move both of these. But note that if I move them together, that doesn't change anything about the solution, right? It doesn't really matter where they are. It just matters where they are relative to one another. For definitional purposes, we're just going to have the general thing, but in order to solve it, I actually don't need to think about moving the outer one. I can just leave it where it is at the origin and only move the inner one. Another thing is that I really only need to think about moving the inner one in the x and y directions, right? If I move it in the z direction, nothing changes about its shadow. These are orthographic projections, no perspective. So I really only need an xy translation or position for the inner one and orientation for both of those. There are several more interesting things to say here, but I want to make this more concrete by actually solving this problem. And it turns out this is quite easy for like the cube and many other simple shapes. So easy, in fact, that if you just choose random orientations and positions, you will luck into a solution. So we'll come back to the interesting facts, but let's talk about choosing random orientations so that we can see some solutions. So if you have a cube or any 3D shape and you want to rotate it around, one of the classic ways to do this is with Euler angles. This is conceptually simple. Take each of the axes in turn, x, y, and z, and perform a rotation around that axis. So the orientation is given by 3 parameters, the amount of rotation along each axis. And these are called Euler angles. The Greeks will call these by a single letter, but pilots will describe these as yaw, pitch, and roll, which I used to have trouble remembering which one is which, but this helpful mnemonic from Wikipedia cleared it up for me. I think cat roll is pretty reasonable, and pitcher is useful because you famously use a pitcher by holding the handle away from you and then pouring towards yourself. But door for yaw is either a really generous dialect or either just trolling me, which I love. I deserve it. Anyway, Euler angles are actually a pretty bad way to do this, especially for computational geometry. Famously, Euler wasn't that good at math, so he didn't know how to do this a good way. And the reason is if you were to sample these parameters, the yaw, pitch, and roll, because this is order dependent, you end up getting a pretty biased distribution of orientations that the object could be in. And this is related to the phenomenon of gimbal lock. So in math and computer graphics, we like to use quaternions, which are the mysterious younger sibling of the complex numbers, even more complex. And so like in the complex numbers, you have I. In the quaternions, you have I, j, and k, and sometimes multiplying those together will give you -1. And then a quaternion is 4 regular numbers, real numbers, x, y, z, and w, which are the coefficients of I, j, k, and then w is the real part. And the cool thing about this is that every quaternion, except for the 0 quaternion, corresponds to a specific orientation of something like the cube. Unlike Euler angles where you have the poles and something special happens at the poles, like gimbal lock, quaternions are sort of smooth everywhere, and this is one of the reasons we like them in computer graphics. If this video doesn't get too long, I will talk about some cool tricks using quaternions, but all you really need to remember is that each quaternion is 4 numbers, so it's like a 4-dimensional vector, and it's often convenient to use unit quaternions where that vector has length 1. And in fact, in order to sample random orientations uniformly, a good way to do this is to just generate random unit 4D vectors. That's the same as saying I want to generate random samples on the surface of a 4D hypersphere. And to get a point on the surface of a sphere, it suffices to find a point inside the sphere and then move it to the closest point on the sphere. So let's talk about how to do that. Now, when I'm sampling stuff, it's easy to get fancy, but my favorite trick is rejection sampling. This is one that's good to have in your toolbox and to just remember. So typically you'll have some function that can sample a number, like a number between 0 and 1. And you could sample two numbers, so then you get a two-dimensional sample. So now I have samples that are uniformly distributed within a square. And then if I want uniform samples from, say, a circle, I put a circle in that square. Or really, I describe the property of the sample that I want, which is that the distance from the origin is less than 1/2 in this case. Remember, I can't fit a unit circle inside a unit square. Then to perform rejection sampling, I just sample from the square, and whenever my point has the property that I want, I keep it, and whenever it doesn't, I discard it and I try again. You can do this for any shape that you can specify as long as it fits within your original sampling region. Now you do waste some samples. So the efficiency of this can be thought of as the ratio of the size of the good region, the circle, to the full region, the square. And for 2D, this is pi/4, or about 79%, which is perfectly good. I'm going to want 4D samples, but first let's look at 3D. Here we have a cube, so I generate 3 random numbers. And this time the volume of the sphere is 4π/3, and the cube is still volume 1. So this gives us an efficiency of 52%, which is also fine. But you may be noticing an annoying pattern here. Not quite upsetting yet. Now if I go to 4 dimensions, I have a hypercube, which is still hypervolume 1. But the hypersphere, which starts to look weird. I know a sphere looks like a 3D circle, like it sort of makes sense. But 4D spheres are weirdly spiky, and the efficiency drops to 31%. This is the fraction of points that fall within the hypersphere when I sample from the hypercube. Now the upsetting thing is that as I go to higher and higher dimensions, the hypercube, the n-dimensional hypercube, will continue to have hypervolume 1, but the n-dimensional hypersphere will get smaller and smaller. Its volume approaches 0, which is totally weird. I don't know how to wrap my head around that, but it is true. So this technique tends towards perfect 0 efficiency in the limit, which isn't great. But my computer can generate billions of samples per second, and I only need 2, so 31% will do fine. We're going to see at least one more example of things getting weird as you get to higher dimensions. But now that I can generate random orientations, let's use it to construct some solutions. So now I can come up with random orientations and positions for the shapes, but I want to test whether I have a solution. And to do that, I need to test whether the inner shadow is inside the outer shadow. Remember that I project all of the vertices of the shape onto the xy plane by just throwing away the z-coordinate. That's what an orthographic projection is. And so that gives me a set of 2D points, and I want to know what shadow that represents. Luckily, these are convex solids, so the 3D solid's shape is determined just from its vertices. And similarly, the 2D shadow is determined just from the set of points. The shape we're looking for here in 2D is called the convex hull, and it's a convex polygon that contains all of the points. Now, you can find a lot of descriptions of algorithms for computing this and computing it efficiently. It's a pretty cool problem. You can also find a lot of slightly buggy code on the internet for computing it. Again, I had to implement it myself. When you're working with these really regular shapes, you end up getting points that are in special positions. And when I'm doing optimization, it sort of optimizes for those situations. And so that tends to find bugs really quickly in other people's code when they were a little sloppy. But just to give you a sense of what this algorithm might look like, let's start with a point set. This is going to be called the gift wrap algorithm, whose name almost describes how it works. So we need to start with a point that's on the convex hull. And the simplest way to do that is to pick the leftmost, bottommost point. So that's this one. Then what I'm going to do is look at every other point and pick the one with the smallest angle, say from the y-axis. And the one with the smallest angle will be my next point. From here on out, the last 2 points will form an edge, and I'll judge the angles with respect to that edge. And so I'll be wrapping these edges, that's the gift wrap, around the outside of the point set. And when I get back to the beginning, the vertices that I found are my hull. That's an n-squared algorithm, but there are nice n log n algorithms for this. Here's an animation of me testing my implementation on a whole bunch of points. And now we can really test whether we have a solution. Take the projected outer points, compute their convex hull using this algorithm. That gives me a polygon. Then look at the inner points, and every single one of those has to be within that polygon.
It's a straightforward matter to test whether a point is within a polygon, especially a convex polygon. So here one of the points is outside, and so this is not a solution. And so that's it, we're done. You can also compute the convex hull of the inner points, and this can be useful because then you only need to test points on the boundary, but it's just an optimization. Speaking of optimization, trying random solutions will work. You can easily find a solution to the cube this way, but rather than starting over every single time, it's better to try to tweak candidate solutions if they're close. For example, I probably could move this one inside or almost inside, and then maybe a little rotation on top of that would make it fit. So the first thing I tried is to use a black box optimizer, which is a nice tool for lazy people like me. And this is a library that optimizes over a function that you wrote. The function you wrote, you might call the loss function. And that thing takes in some fixed number of parameters, which are all just real numbers, doubles, and returns a score. And the black box optimizer's job is to find arguments that will give the minimum score from your function. Now, this is impossible in general. It's literally impossible. We could diagonalize it. But for problems that are smooth, where solutions tend to be close together and there's some gradient, it works quite well. So in this formulation of the Rupert problem, I'll have 10 parameters. I'll have 4 quaternion parameters that represent the outer orientation, 4 quaternion parameters that represent the inner orientation, and then 2 translation parameters in 2 dimensions. And these have some natural bounds. Then I just need some number that indicates how close this is to a solution. So in this function, I check to see whether I have a solution. And if I do, I return like -1,000,000, like a really good number. And remember, it's trying to find arguments that produce the lowest score. So it'll be really happy when it gets a -1,000,000. Otherwise, for every point that's not inside the outer shadow, I take the distance from that point to the shadow, like the closest vector. And I sum all of those distances together. Maybe I square it, something like that. And so the further away the points are, the worse, the higher the number. And so this will encourage it to find configurations where the points are closer to the shadow and ideally all within it. I also have to be very careful about a point landing exactly on the edge because that's not allowed. And I really want it to avoid thinking that 2 identical shadows are a solution. But that's what we call the fiddly bits. So I set that thing running and it can quickly solve all of the Platonic, Archimedean, and Catalan solids for which we already have a solution, thus contributing nothing. We can at least look at the solutions that it comes up with, which is nice. You know, it's one thing to see a claim that the dodecahedron can go through the dodecahedron, but it's another thing, of course, to see the dodecahedron go through the dodecahedron. So here are 2 dodecahedra that are the same size, and they're stacked to show the solution where the blue one's going to be able to pass through the red one by moving along the z-axis up and down. So to illustrate, we can look at them from the very top. Looking down the z-axis. I'll zoom in a little bit. And now see how the red one, you know, basically seeing its shadow here, and you can see that its edge, which is its hull, is entirely on the outside of the blue one's shadow, which is this edge, right? So it's going to fit through if it moves straight down. And in fact, I can swap out the red one for the residue, which is the leftover shape after this thing moves through it. And now if we go back into the side view, you can see that's what's going to be left over. And if I move this shape exactly along the z-axis, it will pass cleanly through it, as expected. So let's just put that on the dry salt bed. The dodecahedron is the best, of course, but it is good to learn about some of the Archimedean and Catalan solids as well. And if you do, you'll see them everywhere. This is the rhomba cube octahedron, an Archimedean solid, seen here at the Cleveland Public Library. So we can do that same demonstration. One notable thing here with the rhomba cube octahedron is that the top one is actually oriented the normal way. It's sitting on its bottom face. This is not unusual for these solutions. It's often, but not always the case, that you want the sides to be parallel to the projection axis, because then when those faces go through, they're not contributing to the size of the hole. We did that with the cube, and we cut a square-shaped hole. All such successes belong on the dry salt bed, this time rendered in mirror and glass to honor the one that I kissed at that library. Bad news, though, you can't see your own reflection in this mirror, and that means you're a ghost. So it's fun to look at these solutions. I guess I could be tricking you here, right? Like I could have made it like 1% smaller. So if you really need to verify them, you could download these from my website, or you could run it all yourself. It's really fast, but I thought maybe I need to make it faster. It's possible that the 5 remaining polyhedra, the ones we don't have solutions for, that the solutions might exist, but be really delicate. So I figured a competitive advantage is that I can churn through a lot of these because, I'm like a reasonably good programmer. I could make a GPU-based solver that would try like millions of them in parallel and just try an enormous number of possibilities. So let's briefly look at what that looks like. In a lot of ways, the GPU is well suited for this kind of problem. Fundamentally, what it does well is take like an array of floating point numbers and do the same thing to them. The GPU can be used for computer game graphics, which I do like, but part of the reason I can justify to myself buying these ridiculous graphics cards is that you can also use them for these kinds of computational tasks. So what I want to do here is try a whole bunch of different possibilities for fitting one shape within the other at the same time. And this is an iterative process where I'll update and make the fit a little bit better over time until I succeed or give up. So I might have like 1 million different configurations, and each one of these is those quaternions which represent the orientation and a translation. And I can start with just random ones. And then for each one of those in parallel, I'm going to check to see if it's a solution. It probably isn't. Otherwise, I'm going to figure out a way to move it so that it'll be a little bit more like a solution. This will give me a new parameter to try, and I can just keep doing that. This is the standard idea of gradient descent. So let's say there are 2 parameters, and you have this topo map representing some function. Here, the function is like how well does one shape fit inside the other, and we don't have 2 parameters, we have like 8. But the goal is to minimize the error. So we're trying to find the lowest point in this map, but we don't know what the map looks like. We just can measure it at any given point. So the idea is we start with some point. We want to look at the local slope around that point and sort of go downhill. That gives us a new point, and we just repeat this process. That idea of following the slope is extremely powerful. This is essentially how large language models work. One problem is I don't quite have the gradient. I have a notion of error, which is how far are the points outside of the hull here. But I'm not good enough at math to work out how those depend on the parameters. And it's not really differentiable anyway, because as soon as a point reaches the hull, its error becomes 0. So problem 1 is that I need to be able to estimate a gradient. And I used a classic crappy trick for this, which is to estimate the gradient locally by computing a few points near each point, like in each of the cardinal directions, and assuming that it's locally linear. This works fine for, say, 2 dimensions where there are 4 cardinal directions, but with 8 dimensions we have like 256. And so instead of doing 1 million tests, I'm doing like 257 million tests. But that's all right, I got a GPU. The other problem is a little bit more annoying, which is that I really want to compute convex hulls of these shapes when I project them to 2D, because that makes it much easier to ask the question, is this point inside that one's shadow? And although I have a nice convex hull implementation, several in fact, these are not very good on the GPU. They have a lot of branching, some of them are even recursive, and like OpenCL does not even support recursion. It really wants you to be writing straight line math code. So that's sort of a downside of the GPU. But we can use its one superpower, which is that it can do a lot wastefully parallel. So what I actually do is I just triangulate the polyhedra. That means every face just becomes triangles, like in a computer game. And so when I project the shape, I just get a bunch of triangles in the plane. And for the other one, the green one, I'm just going to check all of its points, regardless of whether they're on the hull or not. And what I'll be doing is testing for every red triangle, and every green dot is the green dot inside the triangle. And if it's in none of the triangles, then it gets some error to the closest triangle, and this is what determines our gradient. So this is what they mean when they say embarrassingly parallel. This algorithm is very uninteresting now, but instead of doing 65 million clever things, we can just do 128 billion stupid things, and that adds up to the same. Well, not quite the same. There's one interesting complexity here. Remember that a green dot needs to be strictly within the red shadow. That means not on an edge. But now that we've separated the shadow up into these triangles, we have triangle edges that are on the inside of the shadow. And so if a point lands exactly on a triangle, we might think it's actually outside. Sometimes this is unavoidable. Like imagine the cube, if you could imagine such a thing. And I'll just triangulate the top and bottom faces so this is easier to see. Then I imagine that I have a green point somewhere on this line in the center of the cube. So these points, except for the ones on the top and the bottom, are within the cube.
But if I look at this thing from the top, there's no way for that green dot to be inside all of the triangles because there's an edge that goes through the center, regardless of how I triangulated it. So this approach could actually fail to detect a real solution, but that's okay because there's an infinite number of possibilities here, and I'm not going to check them all. And so if I might miss some, well, that's just the cost of doing business. So the solver does work. It's much faster than the CPU version, but it is also kind of warm, uses a lot of power. And I actually ended up using CPU solvers for most of this project because it's sort of easier to do clever things with them. And anyway, I needed my GPU to try other approaches, like the next approach I tried, which was to 100% Call of Duty Black Ops 6. This is not the 6th Call of Duty game. This is the 6th Call of Duty Black Ops game. And to be totally clear, I'm not recommending this game, and this is certainly not an ad. I just feel compelled somehow. I guess I'm a Counter-Strike idiot. 100%ing to me, the multiplayer mode, meant getting all these stupid badges, which for calibration purposes is apparently enough of an achievement for 400,000 views in the genre of I played a lot of video games on YouTube. And then for every single weapon in the game, unlocking everything about it. So you get like 1,000 kills, and then you get 1,000 kills a special way, and then you get this glowing black hole skin. That's really not even that bad, except for these weapons like the baseball bat, which are designed just for humiliating your opponent. Or the rocket launchers, which are meant for shooting down helicopters and for some reason require like a perfect direct hit into someone's soft body to actually kill them. The worst part was these tactical accessories, which seemed to have been designed for a different game. Like this proximity alarm, whose concept art, I assume, depicted a slow burn spy thriller where the sniper is up in his nest, patiently awaiting the perfect moment for the kill, methodically planning for every contingency when the assassin approaches, unaware that the proximity alarm will give away his position and that he is already dead.
Tactical.
Because here's what it's like to play this game. There is no need for help detecting whether there are enemies nearby. There's always 100 guys dressed as Ninja Turtles shooting you with rockets. And you live... I mean, in this game, it's faster to respawn than to reload your weapon sometimes. You spawn and throw a few of those on the ground and then hope that it gives you credit for learning about an enemy first through its beeping, by which time you're usually already dead. Anyway, I played this game for several hundred hours with some of the world's dumbest people. It won't surprise you to hear that when I'm playing, I'm often not doing the game. Perhaps the only thing I like about this game is its treatment of out of bounds. In some places, if you dare to explore, you will be summarily executed. But in most places, it gives you a few urgent seconds to get back into the mission.
That's right, you shithead.
And during that time, you can sometimes do a brief exploration and maybe come back another way, which can be a fun pastime. But the best part is that when the match ends, there's a few seconds of slow motion, and everyone is invincible. You can't be harmed, including, apparently they just don't think about this stuff, the triggers that kill you for leaving the map. And so this gives me, other side quests to my main mission. Like, can I get up on this balcony by timing exactly correctly the end of the match. Or my favorite trick, which is on the yacht level. You're on this tiny boat fighting to the death. And you can get off the boat. You can jump into the water, which normally causes you to drown, like in real life. But if you do that at the end when you're invincible, then you will keep drowning as the credits play, showing you the greatest brutality of the match. This replay's honor is mine, of course. I'm great. All the while, your character is getting increasingly dead. You can actually win the match and be standing on the podium at the same time that you are drowning to death. So that's a good thing to do. But it's all ruined by a single typographic mistake. If you look up here, for some reason, there's a drop shadow behind this text except for this dash. Get it together. Yeah, somehow all that effort yielded no progress on the Rupert problem. But speaking of nerd sniping, I successfully recruited some of my grad school friends, math geniuses David and Jason. Jason made this manual interactive solver, which you could think of as the world's most boring video game. And David, who is a much smarter person than me and has many times cautioned me against trying to work on unsolved math problems, wisely spent his time making soothing animations of the solutions set to electronic music. Having now spent hundreds of hours of CPU time grinding for solutions, we came to believe pretty strongly that the conjecture is actually just false. That it's usually the case that a convex polyhedron has the Rupert property, but that these 5 probably just don't, and that there are other counterexamples. Now, we're not the first to come to this belief, but certainly some caution is due here. Just because it's hard to find does not mean it doesn't exist. And some of the best-known solutions, like, for example, the triachus tetrahedron here, come extremely close to not working. This tiny little thread is 1/1,000,000th of the diameter of the shape. It comes so close, in fact, that you might worry that the floating point round-off in your computer, which is usually something you want to, do machine learning, might be causing you to incorrectly round into a solution. The 3 of us have a background in formal logic and computer math systems. And David actually verified this one in Lean that it does work without any risk of floating point error, which is very cool. And I was spending a lot of my time trying to find new counterexamples to the Rupert conjecture. I call these noperts. Let's say that the theorem is false. That means there must exist some counterexamples, objects that can't pass through themselves, and we'll call these noperts. Maybe those 5 wish list polyhedra are noperts, but there will be infinitely many, almost certainly, because, take the cube, pretend that's nopert. I feel confident drawing it. If you took one of its vertices and moved it like epsilon, or took one of its faces and added a tiny little tent on top of it, it would still be nopert. It would still have the same properties, right? By the way, this operation of adding a vertex and tenting out a face like that is called a kiss operation. And if you look through the PAC polyhedra, you'll see that they have structured names like this sometimes, like the dysdiachus triacontahedron. And sometimes you can tell sort of how they're formulated based on that. Anyway, so there are probably infinitely many counterexamples. Now, if you just generate random polyhedra, which you could do, for example, by taking a bunch of random points and computing the convex hull of those, and just throwing out the points that are inside, these are generally very easy to solve. My solver can solve them in milliseconds. And I tried billions. So the random shotgun method here is just not going to fly. So one of the things I did was use adversarial methods. For example, I could start with a random polyhedron like this one. And let's say that my solver comes up with a solution like this in 2D. Then it's the adversary's chance. And what the adversary will do is try to mess up the shape so that this particular solution won't work. So I could take a random point on the inner hull that's inside, and I could move it until it reaches the outer edge. And now this is no longer a solution. So now I have a new polyhedron that can't be solved that exact way, and I can go back and forth like this, making it harder and harder to solve. And that does work better. Another thing I tried was an explicit de-optimization procedure. So remember I talked about that black box function optimizer that can try to optimize anything, and I'm using that in my solver. It takes a certain number of steps when it succeeds, and so what I can do is wrap that entire procedure in another optimizer call, which tries to optimize the vertices to make the solver take as long as possible, to make it as hard as possible to solve. These two methods do find interesting shapes that are hard to solve, at least with my specific methods. So this lump of coal is one of the products of the adversary method, I think. And for a while I thought that this was a Rupert, but after grinding for a while I did find a solution. It's totally counterintuitive, and it's one of those hanging by a thread, like tooth nightmare ones. This one can't be used for public art installations because it's just too fragile. Okay, well that didn't work. But one thing to notice about the wishlist polyhedra, I mean all of the PAC polyhedra are symmetric, but the ones that I'm generating here are not symmetric. And maybe somehow symmetry is an important component of being a Rupert. So I'm going to try generating symmetric polyhedra, but I learned something interesting and kind of upsetting actually about symmetry. I thought naively that there would be a lot of ways to make 3D symmetric objects, similar to the way that you can use the spirograph method in 2D, which is to pick some n like 7 and divide up 2 pi by 7, so you have a seventh of the circle, and just repeat your points, or in this case lines, 7 times around. And this gives you 7-fold cyclic symmetry. And this does also work in 3D in the sense that if you take that 2D shape and extrude it into a prism, or ninja star, then you get something that has this rotational symmetry. What you can't do is extend that to multiple axes. I naively thought, oh, then I can, rotate it by a third of a turn in another axis. And if you do that, I mean, you get a shape, and it might look cool, but it's not symmetric in the way that you want because these rotations interfere with one another. After doing that 3-fold repetition, it will no longer have the 7-fold symmetry. So if you want to pick a number n and then get some kind of symmetry for it, the ninja star is one way to do that. It's called dihedral symmetry. And it's dihedral because I can flip it over. You could see that it's symmetric around this middle plane. If I make a similar shape that's not symmetric around that middle plane, then this is called cyclic symmetry. Cyclic symmetry reminds me of when my 3D printing site had a contest about coffee, and I noticed a distinct lack of coffee making equipment like the famous mocha pot, which almost has 10-way cyclic symmetry. So I modeled that up and entered it into the contest with instructions for use, but people didn't like it. They said I was doing it wrong. Coffee culture can be so gatekeepy. What were we talking about? Oh yeah, right. So symmetric polyhedra. So you have cyclic and dihedral symmetries, and you have those for every n. And it turns out that there are only 3 more types of rotational symmetry in 3D. There's just no other way to do it. And these are the ones that are enjoyed by the PAC polyhedra. And moreover, and this gave me a real appreciation for how amazing the Platonic solids are, these 3 types of symmetry are in direct correspondence to the Platonic solids. Probably the easiest one to think about is octahedral symmetry, which is the one that the cube and octahedron have. They're duals. And so you probably already know that if I take a cube, I can rotate it 90 degrees on any of the principal axes, and I get back the same cube. There are a few other operations you can do on the cube, like flipping or rotating around its long diagonal. And these are exactly and only the operations of the octahedral symmetry group. So these solids embody these types of symmetry. Several of the PAC polyhedra have this kind of symmetry, like the rhombicube octahedron, which makes sense. It's basically a cube and an octahedron at the same time. And others like the Snub cube, which has cube in its name. Then we have tetrahedral symmetry, embodied, of course, by the tetrahedron. This has symmetry operations like rotating a third of a turn around its central axis, which makes sense. An example of an Archimedean solid that has tetrahedral symmetry is the truncated tetrahedron. This is a tetrahedron that has had its pointy bits lopped off for increased safety. Finally, we have the icosahedral group. You may know the icosahedron as the D20, and I get it if this is your favorite Platonic solid. It's the dual of the dodecahedron, and it's quite lovely. And this has symmetry operations like rotating a third of a turn around one of its triangular faces, or rotating a fifth of a turn around one of its points that have 5 edges coming out. Speaking of point, I'll have you know that video editing is so tedious that I procrastinated making this video by repointing the bricks on my ancient crumbling home at great personal risk.
Anyway, icosahedral symmetry is enjoyed by monsters such as the dysdiachous triacontahedron, which you may know better as the D120, although not many know this shape because only the most advanced Dungeons & Dragons players need to roll with such precision. So speaking of advanced D, this beautiful fact can be extended to higher dimensions. So let's start to characterize some of these. In 2 dimensions, we have the regular n-gons, and each of these gives a symmetry group. In 3 dimensions, we can kind of import those, but let's think about the new symmetry groups that are special to 3D. These irreducible groups correspond to the Platonic solids, the sets of duals, the tetrahedral group, the octahedral group, and the icosahedral group. So there's 3 of those like we just discussed. Thinking about 4D, we have 4 sort of Platonic solids, or polychora. We have a 4D tetrahedron, a 4D octahedron, a 4D icosahedron, and this mysterious self-dual shape called the 24 cell. And each of these has a distinct rotational symmetry group. So that's beautiful. 1 more dimension, 1 more shape, 1 more symmetry group. Can you guess what happens in 5 dimensions? That's right. In 5D, we have only 2 irreducible symmetries, the 5D tetrahedral and 5D octahedral. What the heck? We didn't get any new cool 5D shape, and we didn't even get to keep the ones that we had? That's weird. And in fact, if you look at 6 dimensions, you have only the 6-dimensional tetrahedron and the 6-dimensional octahedron. And so too for 7D, 8D, and all higher dimensions. There's just these 2. Man, if that bothers you, I understand. But you really should be bothered that your own sense of beauty doesn't admit this truth, because this is the true fact of n-dimensional geometry. A true Platonic horror. Anyway, what were we talking about? Oh, right. Generating counterexamples to Rupert's conjecture. So I made some random symmetric polyhedra. You can do this by picking a symmetry group, like the tetrahedral group, then starting with some random points, applying the operations of the group until you reach a fixed point. This is a nice example of a shape with 36 vertices. It has tetrahedral symmetry. You can see I've painted its fingernails there. You can kind of see the tetrahedron inside. And I think that this is a notebird. I've tried solving it billions of times. It doesn't look like any of the PAC polyhedra, so it might be a new counterexample. Here's another one. I've colored some of its faces again so you can see its octahedral symmetry. And again, I've tried hundreds of millions of times to solve this one. This one has 56 vertices, so it's bigger than some of the wish list polyhedra that we already know about. Unfortunately, it's hard to create symmetric polyhedra that have a small number of vertices. When you apply the symmetry operations, it multiplies the number of points. And if your starting points are in special positions like on the axes, then you end up just getting existing well-known solids. Like, for example, I kept trying to find small polyhedra with octahedral symmetry that defy easy solution. And I kept finding ones that looked like this with 24 vertices, which is not bad. But when you look at them, they're all basically the same as the Snub cube. They're just like slightly messed up versions of the Snub cube. And I couldn't find any with fewer vertices. So I began to believe that perhaps the Snub cube is the smallest counterexample. It has the fewest vertices of the wishlist polyhedra. And there just aren't that many simple symmetric polyhedra. But remember cyclic symmetry and dihedral symmetry. This monstrosity has 120 vertices, and you can see its top face is a hexagon, and so is its bottom face. And this has cyclic symmetry, so 6-way rotational symmetry along this axis. The rest of it is kind of a mess, but you can see I have a lot more flexibility there. 120 vertices is definitely not better than 24 vertices. But then I found this. All right, so this bad boy here is potential notebird number 76. And this thing I found after a lot of computer search, and it has 20 vertices. It has 5-way cyclic symmetry with 4 levels, so that makes 20. And I think it's a counterexample to the generalized Rupert conjecture. And I only think that because I've tried like billions of times to solve it with my solver, which works for all of the known ones. But in order to be really confident of that, we would need to actually prove something, which I'd like to do.
This thing has all triangular faces because that's what you get if you just take the convex hull of points in general position. But some of these are really close to being planar. So this pair here is like 1 degree off being a plane. So that's a little bit unsatisfying. And I think it would be an improvement if I could find ones where some of these were quadrilateral faces. So if you just flatten these out, it becomes Rupert. So Rupertness is like a really easy to achieve property. It's very common. But I did a bunch more searching, and then I came up with this one. So this one is Nopert number 214, or potential Nopert number 214. And this one does have some quadrilateral faces. I picked this from a few options because it was the dumbest looking of them. I don't think it's a very pleasing shape unless maybe you like really blingy engagement rings. But it does have fewer faces because some of them are quadrilateral at 27 faces. So 20 vertices, 27 faces. It doesn't get along well with the PAC solids. They maybe feel jealous of it, but they have nothing to be jealous of. This one, its only claim to fame is that it might be a minimal counterexample to the generalized Rupert conjecture if my code is good and I didn't screw up. So I don't really know what I'm going to do with that, but that's true of most of the things I 3D print.
So I wondered if I could make an even simpler counterexample or potential counterexample, because the simpler it is, the easier it is to analyze. And the simplest symmetric shape is arguably a prism. So pretend that's a regular pentagon, so n equals 5, the number of vertices. And when this is really shallow, that is, the depth is close to 0, we know that these shallow prisms can pass through themselves, like a manhole cover that's the wrong shape, falling onto a Ninja Turtle or worker below who should have been wearing a hard hat anyway. Then there's another case where D is quite large, and here we get a long, relatively thin shape, which I'll call a churro. This can also pass through itself, although there isn't a classic puzzle that I can refer to, but I can show you that. So here I'm going to make 2 pentagons, and I hope it's clear that as D gets longer and longer, this same configuration will still apply. So when depth is really small, it's solvable. When the depth is really high, it's solvable. But speaking of pink prisms, there's a spectrum between these points. And it's not clear to me, like, when does a manhole become a churro? And is it possible that there's some place in between where it's neither and isn't solvable? So I looked at that statistically. I took some n like 5 and varied D from basically 0 to basically infinity. And for each depth, I tried solving it a lot of times. And I plotted the quality of those solutions. The quality is like the width of the smallest thread that's left over. You want these to be thicker. It's a better solution if there's more clearance. So here's the graph for n equals 5. Every dot on here is a solution, and I was always able to find a solution. The x-axis is increasing depth to the right, and the y-axis is the quality of the solution, so how much clearance is there. And you can see that there's basically two major sequences here. When the shape is really shallow, all the way on the left, it's almost 0. You get only manhole style solutions. And as the depth gets high, you get churro style solutions. And these cross over right about D equals 1. No doubt you'll notice these peaks, and these represent other kinds of solutions, like where I'm fitting through somehow diagonally. I mean, who knows? If you want to be in a math hole, you would dig into each one of these peaks. Suffice to say, though, for every D, it's clear that we have solutions. I mean, this is not a proof, but it would be astonishing to find a gap given how smooth these curves are. That's for an odd number of sides. The graphs look substantially different for even n. They still have the recognizable manhole and churro signatures, but there are clearly these other classes of solutions that come and go as the depth changes. And I think all of these scattering lines are converging at the square root of 2, which I assume there is some good reason for. For completeness, we can see that there is a crossover point for n equals 3, so these probably all 3 prisms are solvable. We could look at a large n, here 18 gons, and because it's even, we get a lot of this chaos, but there's no trouble finding solutions all throughout the range. So probably all prisms have solutions. But I do think it's notable how chaotic the solution space can get for a shape that's even as simple as these regular 18-sided prisms. It's not like there's just one way to solve it. And then presumably there are a lot of configurations that come close but don't solve it. So this got me wondering, what does the optimization surface look like for one of the interesting polyhedra that might not have a solution? Is it like fractally complex? Or can we make out some structure and see where solutions would be likely to exist? Or maybe convince ourselves that solutions can't exist?
Now, I'd like to do that for the shape that I found, but I actually think that the snub cube is a better choice because it has more symmetries, and it's also a little bit more important to the world. It's completely canonical. So for the rest of the video, I'm going to be focusing on this beautiful 24 vertex shape called the snub cube. We don't have a solution for this. I believe there is no solution, and it's an Archimedean solid, meaning that you can construct it from 3D printed vertices that are all the same, and bamboo sticks or churros that are all the same length, which is cool. So now I have one of those clogging up my office forever. Here's what the snub cube looks like. It's made of squares and triangles, equilateral triangles. Speaking of boring video games, I'm driving my snub cube here with the controller. That's all this program does. Snub cube all the time. I'm drawing the convex hull in yellow. The points of the convex hull are always points from the snub cube itself, and this is always true. And so we're always selecting some of the vertices of the snub cube to form the convex hull. So look at this vertex here. This vertex is currently on the hull. If I rotate the cube like this, at some point that vertex, which is this one, is no longer on the hull. Maybe some other one takes its place, or maybe it's just not necessary. But if you think about when that happens, when does a point go from being on the hull to not on the hull? It can only happen when one of these faces is parallel to our view direction. Then that face disappears and there's a chance for the points to go on one side or the other of it. So what I'm going to do is consider all possible view directions of the snub cube, and I'm going to group them together based on which points from the snub cube are involved in the convex hull. And nearby views are going to have the same set of points, and that set can only change when I cross over one of these planes. And on the snub cube, often there's a face exactly opposite a face. So if you think about one of these squares, the view direction will pass over both of them at the same time. And so really what matters is for every face, we're going to find the plane that passes through the origin that's parallel to that face. Sometimes these will coincide, and this will carve up space into a bunch of different regions, each of which has a different hull topology. Okay, well, that's getting out of hand. If only there was some way to automate tedious, repetitive tasks. So there are 884 different regions of space that yield different hull topologies for the snub cube. I'll call these regions patches, and each one can be identified by a unique code. If you think about all those planes I was trying to draw, you're either on one side of the plane or the other, and so that's a bit, 0 or 1, and that unique bit string identifies where you are in space. You can actually figure out where you are by testing a subset of the planes, because many combinations are impossible. Now, 884 is a lot, but it's not that many for a computer. But even better, the snub cube has octahedral symmetry, and so most of these patches are not even actually any different. They're just looking at the same thing, but like from the other side of the cube. And so it turns out we only have 36 really distinct patches, and the remaining 800 something are just different orientations of those same. If you were having trouble visualizing that from the raw bit strings, we can look at a rendering in 3D. Each one of the different colors here corresponds to one of the canonical patches, and because of the symmetry, they repeat over and over throughout the cube. And here's how to understand the visualization if you want. If you don't want to, just enjoy the kaleidoscope. The color right in the center of your screen, where I've placed the mouse for reference, is the color you would see if you looked from your view position directly at the origin. And so this classifies which patch you're in. If I move a little bit within this blue color, you should see that the convex hull, the points on the outside, are staying the same. They'll move around, but it's the same points. It's when I cross into a different color that the set of points changes. So here when I go from blue to mint, you can see that this point up here is going from being on the hull to not on the hull. Now it's inside the hull. Okay, so worth noticing is that some of these patches are quite small compared to others, and it's possible that a solution would live within one of those. So to explore the optimization surface comprehensively, I'm going to look at pairs of canonical patches, one of them for the outer snub cube, one of them for the inner snub cube, and within those patches I'm going to try a whole bunch of different samples and collect the optimization results. One of the nice things about using these patches is that I no longer need to compute the convex hulls, which is one of the most intensive parts. So now I can do like trillions of these tests with merely hundreds of hours of CPU time. Oh, I can't wait to see how it looks. Oh, well, that is boring. Turns out my first run had a bug. And unfortunately, I had run this in a cluster and refused to look at it until it was done because I didn't want spoilers. So that's $200 down the drain. But of course, my massively profitable hour-long math videos will pay for that. So I'll run it again. And now, yes, that's what I'm talking about. So again, I'm mapping the data onto the surface of the snub cube. Each color represents fixing the outer orientation to that view position, and then considering inner orientations from all over, and making sure to sample from all of the different patches so that I get good coverage of all of the kinds of possibilities. Now, remember that I can always get really close to a solution by setting the two orientations the same. So there are red dots everywhere, but these get kind of blended in with the other colors, which are much more prevalent. For completeness, we could look at it the other way around, where I'm fixing the inner orientation and varying the outer. And this shows the patches prominently for an interesting reason, just having to do with the density of samples. But it does look cool. So back to the good one. What I take from this is that the optimization surface is not really that complicated, right? Most of the time, you're pretty far from a solution. So this led us to believe that maybe we could systematically prove that there is no solution anywhere. So for example, if we pick two of these patches, maybe we could prove numerically that there is no solution when you select from them. And if you did that for every pair of patches, then you could prove that there just is no solution.
Trying hard and failing is not a proof. Let's think about how you could prove that the snub cube is Rupert. So just like we did for the visualization, we can break up the problem into a number of cases. However you orient the snub cube, for the outer one or for the inner one, the orientation will be in one of these patches. And it's fairly straightforward to prove that you only need to think about the canonical patches. There's 36 of them. So that gives us 36 by 36 different cases, determined by which patch you're in for the outer orientation and the inner orientation. So let's just pick one of those cases to see what it's like. Here we know what points the hull is made from, and the points might move around a little bit within some bounds that are determined by the patch. So I don't know the exact shape. The question is simply, can I fit the green one inside the red one? And since these are already 2D, I'm asking whether there's any translation or rotation of the green one that fits it entirely strictly within the red one. Looks like there is. That's just because I drew something. In actual fact, we think there's going to be no way to fit one inside the other. This would actually be quite easy to prove if the points were in a fixed location. If that is, if I had concrete specific polygons. So the challenge here is that these shapes change a little bit as I move around the patch. But the benefit of doing this is that I know a lot about the shapes, and I don't need to worry about computing convex hulls anymore. The outer and inner polygons are determined from the orientations of the 3D shapes, and as we discussed, we can identify those shapes with the view direction within the patch. One decent way to specify this view direction is with an azimuth inclination. So 2 angles on the sphere. Basically, the azimuth tells me how far east-west I am, and the inclination tells me how far north and south I am along that arc. And with these spherical coordinates, you have to be careful not to include the poles because we have the singularities, which we talked about like an hour ago. But these are actually better than quaternions for a lot of reasons with this approach. Anyway, that's easy to do because I have copies of these patches all around. So I'm just going to pick a canonical representative that doesn't include any sort of dangerous singularities. So what it would mean for there to be a solution for one of these cases on the left is I've selected the outer and the inner patch. So I have view directions that are in the outer and inner patch. This gives me an outer and inner polygon. And then, is there a way of translating and rotating the green polygon to put it inside the red one? To prove that this was possible, I would just need to find example parameters that caused this statement to be true, which is nice because then you just need to try one and be right. To prove this statement false, I can't just try a lot of possibilities because I could always have just missed one. So how could you prove something like this? One good approach is interval arithmetic. So let's extend the scope of the video further to talk about that. Let's collect together all of the parameters that we're considering for one of these cells. There are 7 parameters, of course, and each of them has finite bounds. This means we can think of the parameter space as a 7-dimensional hypercube, if that helps, where each of the dimensions is one of these parameters. And we're trying to prove that nowhere in that space is there a configuration that leads to a solution.
So I can at least draw a 3-dimensional cube. So let's pretend there were 3 parameters. We could never cover this cube by looking at individual points one by one, but we could cover it with volumes. The idea is that we can think of these parameters as intervals, that is not a specific point, but a range of possible points that are contiguous. And I can still do math on intervals. Like as a really trivial example, if I know that the azimuth is between 0 and 1, then the azimuth plus 1/2 is between 1/2 and 1.5. So I'll start with each of these parameters taking on its full range. The interval will be the full range. So the volume is the entire hypercube. And then using intervals, I'll compute sort of where are the polygons and see whether the one is in the other. And I won't be able to tell because there's going to be so much uncertainty about these because I'm using these wide intervals. But that's fine. I'll just pick one of the dimensions and I'll bisect. So now I have 2 volumes that are smaller on that one dimension. So I'll recurse on one of those. I'll have to do both eventually. And these are also still way too big. So I'll bisect on some other dimension, which will still be too big. So I'll bisect on another dimension. And I'll keep doing that until I have bounds on the locations of the points of the polygons with decent certainty. With bounds on the points, I can sometimes tell that one of the green vertices has to be outside the red polygon, even though I don't know quite where they are. This will be the case here. So that lets me check off this possibly quite small volume that's part of that 7-dimensional hypercube. And if I can cover the entire hypercube, then I know that there is no solution in that cell. Now, I don't know why I drew you a schematic version of that. I did implement this, and I can just show you what it looks like as it's running. I like watching this because it reminds me of those cop shows where it's just gratuitously flipping through all of the fingerprints as they search the database for the killer. There are multiple ways to prove that it can't be done for some set of parameters. For example, I could compute the area of the green one, bounds on the area, and see that no matter what, it's not going to fit in the red one's bounds. There are also a lot of engineering issues and numerical issues. For example, we want to be really accurate with these, right? So no floating point round off. And the volumes can get quite small. So I'm using arbitrary precision rational numbers for everything. And so when I compute sine and cosine, I need to be able to compute bounds on that using the Taylor series. And I don't want the fractions to just keep getting bigger and bigger and bigger, like larger and larger denominators. So there's various tricks you can do to use simpler fractions. It's all very, very cool, but I could easily do an hour on just the techniques used in this program. But I want you to at least take away that interval arithmetic is not simply a matter of doing algebra on the endpoints, like doing the algebra twice. Because I think this is a characteristic difficulty and is interesting. Okay, so each interval is a lower bound and an upper bound. And if I want to add 2 intervals, it does in fact work the simple way, which is to add the lower bounds, add the upper bounds, and the result is that. Because the smallest result you could get would come from adding the 2 smaller values and the largest from adding the 2 largest. And multiplication is not much more complicated than that. The main thing to realize is that the extreme values of the output, which is what we're trying to compute, will happen at extreme values of the inputs, but not necessarily in the same order. If I have the interval 2 to 3 and I multiply it by an interval that's just -1, then I get -3 to -2, so they get swapped around. So I basically compute all the endpoints and do a min and a max over those. The interesting thing happens when I have formulas that use the same interval more than once, and this is called the dependency problem. A really simple case is where I have an interval z times itself, so z squared. On this example, -3 to +2. If I square that using the multiplication formula, I end up getting -6 to +9, because I have to consider the possibility of +2 times -3. But z is describing some actual number that's in between -3 and +2, and anytime I square one number, I get a positive result. So although -6 to +9 is a correct interval, it contains all the possible values, it's pretty lossy. The best interval for z squared here would be 0 to 9. This is the essence of the dependency problem. It's not just about squaring. Anytime a variable appears multiple times in some algebraic expression, by default, you lose the dependency between that variable and itself. So terms fail to cancel, for example, and you get intervals that are way too wide for what you're trying to do. So for this problem, I didn't just have to re-implement the solver with intervals. I had to think really carefully about the algebraic formulation of these tests to minimize the dependency problem. But I mean, that just means you have more interesting problems to spend your life on. Speaking of interesting problems, the last thing to be aware of with this proof approach, going back to the matrix of the patches. This approach does work when the green and red polygons are always substantially different. Then I'm able to find some subdivision where I can prove that it can't work. But on this diagonal where I've selected the same inner and outer patch, this includes parameters where the inner and outer view are exactly the same. And thus the red and green polygons are exactly the same. Now when they're exactly the same, I know that I can't fit one within the other. That part's definitional. But near the diagonal in parameter space, it's going to look like I'm close to a solution. And the interval approach will just keep subdividing. It seems like it's impossible to actually rule these out. And this case is truly hard. We saw before that sometimes proper solutions can be extremely close to the diagonal. And I'll give you one more example of that kind of thing. Suppose you just have a square. It turns out the square can pass through itself, which is not at all surprising. What's maybe a little surprising is that it can pass through itself arbitrarily close to this diagonal. First, just rotate it epsilon along this axis in 3D, and then by 3 epsilon in the other axis. The resulting trapezoid does fit back within the original square, and I can do that for epsilon as small as I like. Now this shape is infinitely thin, but we can make it into a proper polyhedron by just using the kiss operation to add a little tent. And now we have a really problematic shape. Now I don't think this ever happens for the snub cube, but in order to complete the proof, we do need to do something about the diagonal. So let's work on that. Well, Christmas is canceled. I figured I'd capture this moment, this momentous occasion where we were scooped. Jason just found a paper by some guys that had emailed me before, of course, and I probably should have written them back. Turns out they were also working on this problem, and they proved that there exists a polyhedron that does not have the Rupert property. They call it the noperthedron. Noperthedron. You probably know perthedron. I like to think I influenced that name a little bit. Here is the aforementioned hedron. And this is a shape that they created specifically to prove that it's a nopert. And this Donkey Kong barrel has 30-way cyclic symmetry with 90 total vertices. So certainly I think there are smaller, simpler noperts. And maybe that's something left to do, but they were the first to demonstrate a shape that was definitely nopert. And they independently came to a very similar approach that we were using, which is to do this large-scale computer search for the sort of coarse case. And they have some separate machinery for the diagonal, which they call the local theorem. But their techniques won't work out of the box for the snub cube. They require a certain kind of symmetry, point symmetry, around the origin for the shape. And this allows them to cut down the search space to 5 dimensions from 7. That part actually seemed like it was working pretty well. I mean, this is what it looked like on the morning that we found out about this. So I think the 7 dimensions is actually very feasible. But I think we would need some kind of new local theorem in order to actually make the snub cube proof work. Anyway, congrats to the authors. That whole time I was worried about aliens also being concerned with this problem, but it was really Austrians. But I think in the time that it took me to set up the camera, I'm already over it. Because I have a lengthy list of other exciting projects to work on. And I can just stop any time I want with the cubes. I just stop working on it. It's already solved. So easy.